So acceleration, we covered velocity so far. Acceleration, so this is defined as a change in velocity divided by change, the time taken for the velocity to change, basically. So in velocity divided by the time taken for velocity to change. So this can be, you can write that as the final velocity, which we can go, so minus divided by the time taken, which you can, so time t minus time 1, basically. The final time minus the initial time, okay? So you take the initial velocity at time 1, the final velocity at time 2, and that gives you your time 1, time 2 initial and final velocity. So acceleration, you can basically write it as basically velocity 2 minus velocity 1. You can write it like that. So final velocity minus initial velocity divided by time 2 minus time 1. So you take the first velocity at time 1, say when time equals 0, and the second one at, say, time equals 5 seconds. And it's as meters per second units, okay? So every second, the acceleration means that for every second that passes, the velocity changes at 1 meter per second. When the acceleration doesn't change, you have constant uniform acceleration. Okay, so constant to uniform, it's gravity, for example, is generally at 9.81 meters per second. So if you go up 100 meters in the air, it's the same it's the same acceleration everywhere. So it's a constant uniform acceleration. So this means the velocity is changing, it's increasing 5 meters per second every second, okay? So the velocity is changing 5 meters per second every second, okay? That's what 5 meters per second means. So at rest, the velocity equals 0. After 1.0 seconds, the velocity equals 5 meters per second. After 2 seconds, the velocity equals 10 meters per second. Okay? 3 seconds, the velocity equals 15 meters per second. So if it's changing at 5 meters per second, that means after 1 second it's 5, 2 seconds it's 10, 3 seconds it's 15. And so if it's changing every second by 5 meters per second, after 10 seconds it will be 50 meters per second, okay? So 1 second it's 5 meters per second, a second later it's 10 meters per second, a second later it's 15 meters per second, a second later it's 20 meters per second, and after 10 seconds it's reached 50 meters per second. So that's what acceleration is. When acceleration slows, this is called negative. negative acceleration, okay? So, negative acceleration. And when it's increasing, it's positive acceleration. So, minus 2 meters per second equals, that means the velocity is decreasing by 2 meters per second every second, okay? So that's what a negative acceleration is. If it's minus 5 meters per second means the velocity is decreasing by 5 meters per second every second. So that's a negative acceleration. So if you're in a car that's going along a motorway at 70 and you suddenly have to ram the brakes on, if you see a crash or something in front of you, or there's suddenly roadworks, if suddenly something happens and you have to ram the brakes on, gently initially, and then as you lose speed you push them harder. You shouldn't ram them on full at the beginning because you could actually skid and go out of control, but if you do it quickly, the acceleration should rapidly drop from 70 down to 60, 50, 40, 30, 20. Should rapidly drop 70, 60, 50, 40, 30, and then you can ram them on. So it's probably losing about maybe 15, maybe 10 meters per second every second, or 15 meters per second every second. And then gradually it will increase to maybe 25 meters per second every second, and you'll quickly go down to 0 miles an hour, to 0 meters per second. So acceleration is it's a vector quantity. Okay? So it requires direction and length. And size. Okay? Requires direction and size. Acceleration is represented by 2 arrows, whereas velocity is represented by 1. Okay? It's a vector quantity. So a change in vector, when you have a change in vector, equals the final vector minus initial vector. Okay, so we can go minus initial. So we call it change in vector. Vector final minus vector initial. Okay. Whereas the change in the scalar, I said before, scalar is just a quantity. There's no direction, it's just a quantity, a number. That equals the scalar, I call it scalar final minus scalar initial, okay? I'm calling it S scalar because S can be other things. So change the scalar is initial, the final scalar minus initial scalar, scalar. Okay. If you have an example, you know when you get overhead TV satellites, okay? Satellites orbiting the Earth. So these go around the Earth at constant speed. But because the direction of travel is always changing, okay, so if they actually went off in a straight line, they would end up shooting off into space. So the direction is actually always changing like this. They have to be constantly changing direction. And because of this, they because the direction is always changing, the velocity is constantly changing. Okay, and because of this, they're actually accelerating. So yeah, the direction changes, and because the direction has been changed, the velocity has been changed. So it's actually accelerating. Yeah, as the satellite moves around the planet, it's constantly being pulled by gravity. The force pulls on it, causes a change in the velocity, so it's constantly being incrementally accelerated. Okay, so it's actually, although it's constant speed, it's actually accelerating. Okay, so there are different kinds of velocity and acceleration curve, or okay, graph. So you get okay. So there's various kinds of graph here. First one is the velocity remains constant, so it's constant velocity. The velocity doesn't change. Second one, the velocity is constantly changing, so it's constant acceleration. The velocity is continuously changing, so it's constant acceleration, okay? Because the velocity is changing all the time as time progresses. This one is the reciprocal of that. The velocity is continuously decreasing, so this is constant negative acceleration. The velocity is slowing with time. This one, unlike this one where the velocity starts at 0, okay, here the velocity as you start is already, the object's already moving, say a car moving at 10 miles an hour, so this is constant acceleration because the velocity is continuously changing, but it's already moving. So say starting at 10 miles an hour and then suddenly you start pushing on the accelerator to speed up. This one is two accelerations, but the acceleration of x, this one, is greater than the acceleration of y. So velocity of both is constantly changing, but this is continuously changing, not constantly, continuously, but the acceleration of x is greater than the acceleration of y. And this represents displacement. So if the units are, velocity is meters per second, okay, times time, which is seconds, okay, so these both cancel and you're left with meters, which is the displacement. So the area under the graph is actually the distance you travelled, okay. So it's meters or miles. So yeah, it's miles an hour divided by hours. The hours cancel and you're left with miles, which is the displacement, the distance travelled of the displacement. Okay, I hope that makes sense. That's just graphs, but that's what graphs look like. It's always better when you're doing studies in this. It's always better to actually do proper experiments and measure the time of things, and but this is what the graphs would look like. So next one, if you're trying to work out the area of a graph like that, how can you do that? So you can either, one way of doing it is to divide it into lots of strips and work out the area of each strip, or if you know, if it's constant like this, if that's a constant velocity, work out the height and the length and time, multiply them together and it gives you the area. But you can't do that normally if you have a graph like this. So you can't, if you take sort of intervals of time like that, okay, you can't really work out the area of each of these strips because they're all different and it gets a bit difficult. So what you can do is you divide it into two triangles and this, okay, so you get the area of that and then work out the area of the triangle by half base times height, okay? So you work out the area of this and the area of this, half the base times the height, add it onto the area of this, which is just height times base, height times length, and you get your total area, okay? There's another way which you could do as well, which is a bit more tricky, but if you have so like that, okay, and you want to work out the area, you can obviously work out the area of that part by going length base times height. But if you've got these sections here, okay, what you can do is you can divide each of these strips into say 1 millimeter lengths, and work out the height. So if you divide it roughly in say 1 millimeter lengths and then multiply each millimeter by the height, okay, it will give you an approximation, and you add them all up, it will give you an approximation to the area of the triangle, and the area of this part here, and the area of that triangle there. You could obviously do it for that square bit, but you as well just use this because this is more accurate. This is a method that comes into higher maths, okay, and it's actually part of calculus. Okay, so if you're taking 1 millimeter lengths, it's difficult to take shorter than that, but if you do base 1 millimeter times the height, it would give you an approximation. Well, it would only give you the lower height, but if you took the lower height and the upper height and you took an average, you could get a rough approximation to the area. But in calculus and higher maths, you learn a more refined version of what I'm describing, which is actually much more accurate than even this. Well, it's probably as accurate, but it's more useful than this because what you learn lets you work out the area of grass like this, which would be impossible even by this method. So this is useful when you've got straightforward triangles and rectangles and squares, using the area of a triangle. But if you've got a curve like this, you can't use that, all this. So calculus lets you work out the area underneath this very accurately, but even much more refined, specialized techniques which are introduced at high grade, okay. Anyway, back to mechanics. So so this is the way to work out the area of a curve that sort of where velocity increases and then goes constant and then decreases. So examples. If you have a car, okay, velocity equals 0. So initial velocity, final velocity equals 25, time equals 12 seconds. The car is driving in a straight line. Okay, so the acceleration equals velocity, initial velocity, you should call that I. Final velocity minus velocity initial divided by time, which equals 25 minus 0 divided by 12 meters per second, okay, which gives you 2.1 meters per second minus per second, okay, 2.1 meters per second. So the acceleration of this car is 2.1 meters per second. So this is how you apply it. Apply the formula. Take your initial velocity, the final velocity, and time taken, and final velocity minus initial velocity divided by time taken, and put this through the calculator to the sums. Next one, lorry travels in straight line. These are really boring examples, okay? Or planes traveling in a straight line. But it slows down uniformly, okay? So travels in a straight line like this, but it slows uniformly. Okay? In the same way that this, I suppose, is slowing uniformly and comes to a full stop. Like that. It's nearly stopped. Too much rolling. It doesn't want to stop. That's it, stop, see? It's probably slowing down fairly uniformly. There we go, it stopped. This table is not level. It's actually going backwards, the table's not level. I know that because it's not staying still. So, slows uniformly from 15 meters per second to 2 meters per second, okay? This takes 12 seconds. Calculate the deceleration. Okay, so acceleration equals, it's deceleration, so that the final velocity is actually, so it's velocity final minus velocity initial divided by time taken is equals actually 2 meters per second, okay, minus 15 meters per second divided by 12 seconds, okay, which gives you minus 13. You have to remember the minus because it starts off fast and becomes slow. It's actually negative. It's losing speed, so it should be negative 13 divided by 12, okay? Which gives you minus 1.08. That's meters per second squared, okay? Meters per second squared. So minus 0.018. So yeah, that's deaccelerating minus 1.08 meters per second over 12 seconds. So the initial velocity is 15, but the final one is actually 2 in this case. So yeah. Next example. That next example. Yeah, you got so okay, so if you have a time velocity starts at A, goes to B, and goes down to C, okay? That should be a straight line. That's 0, okay? And that's 10, and that's 6, okay? So this is a case of, call it a plane or something. So from A to B, this is constant velocity. From B to C is constant negative acceleration. From, sorry, that should be 18 there. From 18 meters per second to 0 meters per second, okay? So 18 meters per second down to 0. 18 along here and then falls down to 0 meters per second. And it takes, that drop there takes 4 seconds. Okay? So that's one. So calculate the acceleration from B to C, okay? So your velocity final minus velocity initial divided by t, which equals final is 0 minus 18 divided by 4, which equals minus 18 over 4, which equals minus 4.5 meters per second minus 2, okay? Okay, so that's the acceleration, the negative acceleration, the deceleration is minus 4.5 meters per second. And the average velocity is, so yeah, to be clear, from A to B, the motion is constant velocity, okay? From B to C, it's negative acceleration from 18 down to 0 in 4 seconds, okay? To calculate the average acceleration from B to C, it's the final acceleration, final velocity, which is 0, minus the initial one, which is 18, divided by 4 seconds gives you minus 4.5 seconds per meters, minus 4.5 seconds meters per second. So the average acceleration is minus 4.5 meters, or minus 4.5 meters per second. So every second that passes, you slow down at you slow at 4 meters per second, okay? It's slowing. And then finally, how do you calculate the average velocity, okay? So, how to calculate the average velocity? So, it's moving, it moves in a straight line. It doesn't change direction. So the displacement and the distance is the same, okay? So it slows down, the displacement, which is basically the distance, is the same. So the displacement is basically the area under the graph, okay? So it's actually the total, the average velocity is actually the area of this plus the area of the triangle, okay? Area squared, area of the triangle. So to work out the area of both, it's the, to work out the average, I'm not saying this very well, to work out the average velocity, you have to work out the displacement, total displacement divided by the time, okay? Because this displacement and you work out the displacement divided by the time gives you the average velocity. So to get the displacement, you have to work out the area, and then you work out the average velocity, displacement divided by time. So making a bit of a mess of that. So displacement equals the area under the graph, okay? Which equals area square, area of 1 times area of 1 plus area of 2, okay? So it's area of 1 plus area of 2. So the area of 1 is the square, which is 18 height times 6 length, okay? Plus area triangle, which is half base times height, so it's 18 times half 4, okay? So half times 4 times 18. That's 6 to the 10 is 4, and that's height is 18. So it's so 18 times 6 is 108, 6 8s are 48, 6 1s are 6, 7 8 9 10, plus 2 goes into 18 9, so 9 4s are 36. So you get 144. 30, okay? So the total displacement under this is 144 meters. So the object, say a snooker ball, is moved 144 meters from A to C, okay? Or football, or bicycle. So the average velocity equals the displacement, this divided by time taken. So we know it's 144 meters. Okay, divided by a total of 10 seconds. Okay, 0 to 10. So that gives, you can just move the decimal place one place to the left, so it goes 14.4 meters per second. Okay, so that's the average velocity. So I hope you understood that. The average velocity is the displacement, the distance covered in number of seconds, so it's distance per time, per unit time. And you get the displacement from working out the area of this and the area of that, and the area of this is length times width, 18 times 6. And the area of the triangle is half base times height, so it's half times 4 times 18, which gives you 144. And then 144 divided by the 10 seconds gives you 14.4 meters per second. Okay. So yeah, that's another example. We just had Easter. So an Easter egg rolls down an Easter egg rolls down a hill in a straight line. In theory, although they always usually bounce around. Sometimes they don't go very far, but it should roll down a hill in a straight line and accelerates uniformly. Okay, we'll make it a football. Easter eggs don't really do that because they're shaped like ovals and they bounce around. They don't roll very well. Let's make it a football, okay? Or even a sledge going down the hill. A sledge is going to roll straighter and more evenly than an Easter egg. Make it a sledge. So it goes from 1 meter per second to 3 meters per second in 10 seconds, okay? I could go quicker than that, but it's just numbers. It's more likely to go from 1 to about, sledge would be about right, maybe 1 to perhaps 3 or 4, that'd be about right for a sledge maybe. So, calculate the average velocity. So, it equals 3 calculate the average velocity. So in this case you have, to get the average velocity, this isn't to work out the acceleration, which is final velocity minus initial velocity. It's just to work out the average velocity, which is, I'll say it again, it's not to get the acceleration, which is final velocity minus initial velocity divided by time, but this is the average velocity, which is actually 1 meter per second plus 3 meters per second, okay, divided by 2, because there's 2 of them. So that equals 4 divided by 2, which equals 2 meters per second, okay? If you were to increase, if you're going from 1 to 3, and then went from 3 to, so you understand that's the difference. This isn't a acceleration where it's final velocity minus initial velocity, it's the average velocity. So if it goes from 1 meters per second to 3 meters per second and then accelerates again to say 6 meters per second, and so if that takes 10 seconds and that takes another 10 seconds, then what's the average velocity? It's equal to 1 plus 3 meters plus 6 meters divided by 3, which is 6, 7, 8, 9, 10. Okay? Which equals 3.3. So, when you're taking averages, if there's 2 numbers, you divide by 2. If there's 4 numbers, you divide by 4. If you've got 10 numbers, you divide by 10. Because it's the average, it's not divided by 2. It's divided by the total numbers. So yeah, when you have an initial velocity of 1 meter per second and a second one 10 seconds later, say of 3 meters per second, the average velocity is 1 plus 3 divided by 2, which gives you 2 meters per second. 1 plus 3 is 4, 4 divided by 2 is 2, which is 2 meters per second. But if you have, say, a third velocity, if the sledge, say, increases from 3 to 6 meters per second 10 seconds after that, so what's the average velocity of these three? It's 1 plus 3 plus 6 divided by 3, which gives you 3.33 actually. Okay? So you divide by the number of variables you're adding up, okay? So if you have 10 numbers, you divide by 10. If you have 10 separate velocities, you have to divide by 10, okay? If you don't do that, you can find that the average speed is actually, say, bigger than any of the velocities you have. So if you have sort of 1 plus 3 plus 6 is 10, 1 plus 3 plus, if you have 1 plus 3 plus 6 plus 7, say, 1 plus 3 plus 6 plus 7, so if you go 1 plus 3 plus 6 plus 7 and divide that by 2, you actually get an average of 8.5. Well, that doesn't make any sense because it's nonsense. If these are all velocities, how can the average velocity be faster than each of the velocities? Okay? So you record 4 velocities, the average one is 8.5. How can it be quicker than any of the recorded numbers? So that's nonsense. So you actually divide by 4, and then you get 1 plus 3 plus 6 is 17 divided by 4, which gives you the correct answer of 4.25. So the average velocity of, if you take 4 separate velocities as a sledge goes down a hill, the average velocity is 4.25, which is correct because it's the average. It's sort of the intermediate value between 1 and 7. It's the average is the middle sort of number. So it's the middle velocity. It's the intermediate. It's the velocity between the numbers, which is the average. It's sort of statistically the one which is halfway from between the first one and the last one. So yeah, but as I said, you divide by the number you have. So if it's 5 numbers, you divide by 5. If you divide by just 2, you end up with a number that this is nonsense because it's outside. It's faster than any of these. Okay. Okay. Right. So that's the reason why you can yeah, so the average velocity is calculated using these because acceleration, although the sledge is actually accelerating, you can use this equation which is equals the velocity 1 plus velocity 2 or velocity 1 plus velocity 2 to velocity n divided by n. You can use this because acceleration is it's a constant. Okay. Right. So from acceleration, we're going to go on to forces. Okay. So the force of an object is actually equal to the mass times the acceleration. That's Newton's second law. So, which is what I demonstrated when I was banging these into each other. So forces speed up or slow down. okay? And they change direction of moving objects, like I just demonstrated with these they change direction of moving objects, okay? As with the satellite going around the planet, I showed the force, gravity changed its direction. Otherwise it would keep going in a straight line, go off into space. It would go way out like that or way out like this, okay? And they can also change shape. So if you have a force, take a sponge. If I press it, it can change shape, okay? I can make it into a small object like that by compressing it. So that's force acting on something soft. Or I can take this polystyrene and press it, okay? So the force, if I press down it changes shape, okay? Or if I take a spring like this, it's actually an egg cup, but this is basically a spring. You can make the shape change with a force. I can compress it down, and it changes shape, okay? Pull it apart and it will spring back, okay? So the spring is actually used, this is a small spring I've got, so you can, springs are actually used to measure forces. This is little, I need a bigger one, but they're used to measure it. So if you have a spring, okay, and you have a particle at the end, so with the mass in kilograms, okay, so if you have a spring's way of measuring, if you have the mass of objects do not, any object like a hammer or anything you have is made of mass and it has weight, but this actually changes depending on the gravity. So a hammer might weigh 0.5 kilograms on Earth, but if you go to the moon it will actually weigh less because the gravity is not so strong, so the force acting on it is much less. So you have if you have the force of gravity weighing down on the ground, okay, this is a mass, okay, gravity is the weight of the object, okay, so the weight my point about the hammer is the weight of an object on Earth is greater than the weight on the moon, okay? Because it's a low gravity. So if you take anything to the moon, it will weigh a lot less. And in space where there's no gravity, nothing has any weight. So astronauts can move satellites with a single hand and arm that maybe weigh 4 tons on Earth, but they're weightless in space, so they can actually pull it in and out and move it. The weight of objects and the masses give the gravitational field strength. Okay, so the weight of object, the weight divided by the mass of the object, equals the gravitational field strength, which is a constant, okay? It's a constant G, okay? And it's given by, it is units, which is newtons per kilogram, okay? And on our planet, this is actually given by 1 kilogram weight, okay? So, 1 Newton equals 1 kilogram, I think that's right. So you got the weight of an object is actually mass times G, but that's kilograms, and that's newtons kilogram, okay? So these both cancel out to give newtons. So I hope this is getting slightly confusing. I just have to go over this and let you absorb it. So on Earth, the gravitational field strength on Earth is okay, so that's the weight. The gravitational field strength is 9.8 newtons per kilogram, okay? So 1 kilogram weight has weight 9.8 newtons. 10 kilograms has weight 98 newtons, okay? 1,000 kilograms has weight 9,800 newtons, okay? I should say force like acceleration is a vector quantity. And yeah, as I said, force is equal to mass times acceleration, and acceleration is vector, okay? So it's basically vector because it's a product of mass. Sorry, it's a product of acceleration but also mass. So you have mass is kilograms times accelerated meters. I'm thinking of vector. Forget that. This is a vector quantity, so that because that's a product of this is a vector quantity because mass has no connection to vector. That's just that's actually scalar. Okay, so yeah, so when you have if you have an object and you have two forces acting on it, that might be, that's 10 newtons and that's 6 newtons. They're both moving it, that with 10 newtons to the right and that's with 6 newtons to the right. If you have another object, y, so in this case that's moving at 10 newtons to the right, well that's moving at 4 newtons to the left, okay? That's the left, that's the right. So forces, it can push objects in different directions. I'll come back to this next video and carry on with it. But basically, I think the key points are the weight of an object divided by its mass gives you a G, which is a constant, and that's in newtons per kilogram. So I'll yeah, and you can work out the weight from the mass times G, so I'll leave that with you for the moment.